All right, we're recording. And we're going to start chapter 11 today. Now, I put together a booklet, and I did this last year when we kind of ran out of time because it was, we lost classes because of the whole COVID thing. So we're not going to do all of chapter 10. We're only going to do 10.3. And last year I put 10.3 at the beginning of chapter 11. Talking to my colleagues, they want to go right into chapter 11 first. So we're going to skip this first part of this booklet where we start with 10.3. We'll do it at the end if we have time, which I think we should. So we're actually going to start here on 11.1 and 11.2, which is kind of rolled into one lesson. We may not finish it today. We'll start it today. We'll finish it tomorrow, called the Fundamental Counting Principle. And before we actually tackle that, let's do something fun to start with. Remember the 4 4s puzzle? For example, if you have 4 4s and you can use any operation you like, you can make the number 0 by going 4 plus 4 minus 4 minus 4. There you go, that's 0. Of course, you could make a more interesting 0, perhaps by putting the 4s together like this and getting 0. Or you could go 4 divided by 4 minus 4 divided by 4 is 0. Or here's a fun one. You could go 44 times 4 minus 4 is 0. Of course, the whole point of the exercise was not just to do 0. You were supposed to do all the numbers from 1 to 20. That was the puzzle I left you with. And I did revisit it once in class where I mentioned to people, okay, what numbers are going to be tough? Because some of them are actually quite easy. 13 is actually fairly tough. Here's one way you could do 13. You could concatenate the 4s into 44, divide by 4. There's your 11. So you only need 2. How do you turn a 4 into a 2? Aha, there you go. Used 4 4s to make 13. Somebody else noticed that 19 is kind of tough. Did anybody find a way to do 19? How about I ask and see if anybody here wants to volunteer a 19? 19 can't be made if all you have to fall back on is concatenation like this, division, multiplication, add, subtract, square rooting. You have to get fancier than that to get 19. So here's one way you could do 19. Do you get why that's 19? Because 4 divided by 0.4 is 10. And this is 4 divided by 0.4 repeating. 0.4 repeating is 4/9. So that's going to be 10 plus 4 times 9 over 4. And there you go. There's your 19. So that's one way you can make 19. Another way you can make 19 is by doing this. You could go and that introduces us to our new symbol today. What the heck is this? It's like I'm yelling, 4! It's an exclamation mark. 4, the musical. What does that symbol mean? Well, oh, hang on a second. I'm going to move this down for a sec. You're not supposed to see that yet. There we go. 4 factorial is what we call that. And that is 4 times 3 times 2 times 1. So in fact, 4 times 3 is 12, 12 times 2 is 24, 24 times 1 is still 24. So this is really 24 minus 4, which is 20, 20 minus 1 is 19. And this factorial allows you to do, well, lots and lots and lots of cool things with this 4x4 puzzle. In fact, tell you what, I'll let you challenge me. Pick any number. I told you to go from 0 to 20, and we already did 0 together. And now I've shown you the toughest one, which was 19. Pick a number between 20 and 100. Any number you like. And I'll make it, now that I have this factorial. Somebody in the chat, pick a number between 20 and 100. Anybody? Throw a number in the chat. 97. 97 is a good number. So 97, I'm going to go 4 factorial times 4 plus the square root of 4 divided by 0.4. So 24 times 4, what is 24 times 4? That's 96. No, it isn't. What is 24 times 4? 80 plus 60. Oh, it is, yeah, it's 96. 80 plus, so that's 96 plus, and then this is 9, square rooted is 3. So there we go. 96 plus 3 is, oh, that's 99. I'm sorry, you said 97. I'm sorry. You wanted, that's 99. You wanted 97. 97 is 4 factorial times 4 plus 4 over 4. There we go. 96 plus 1 is 97. There we go. So there we go. You get the idea. Having said that, you know, with all the tricks I've been doing using, oh, sorry, this is supposed to be a repeating. Forgot my repeating symbol on that. For all of my tricks where I'm using decimals and repeating symbols and square root signs, and now I'm using my factorial symbol, there's actually still a number between 1 and 100 that you can't make with any of these tricks. And weirdly enough, it's the number 61. Then, and of course, people would challenge each other to make numbers in the hundreds and in the thousands and find all kinds of neat tricks. But 61 wouldn't yield. And then along came a physicist who said, not only can I make 61, I can make any number you like. So people were kind of, this was a very popular pastime for a while in a newspaper puzzle column, until along came a physicist to spoil everybody's fun by saying, I've kind of cracked this puzzle, and I can make you any number you want. Any number at all. From 1 to infinity, just using 4 fours. And this was what he showed. His name was Paul Dirac. He was one of the physicists who worked on the Manhattan Project that created the nuclear bomb for World War II. Here is what he came up with. So I'm going to leave that with you. I mean, it's not a puzzle class unless I actually leave you with a puzzle. So jot that down, or take a screen cap of it, and then A, see what the answer to that is. And then B, how does this lead to being able to do any number you'd like? So I'll give you maybe a couple days to play with that. Maybe Thursday or Friday I'll come back and we'll solve that puzzle. So there we go. We solved the puzzle, we solved the 19 riddle, but I'm leaving you with a puzzle. What does this equal? And then, how does this crack the 4x4 puzzle? So there we go. Take a screen cap or jot that down. You know, one other thing I wanted to do today, since we're doing puzzles, again, we'll see, on Friday I'll solve this for you too. Since we just finished a unit on logarithms and exponents, here's a beautiful exponent puzzle I saw on the internet the other day that I'd never seen before. Take a screen cap of that and see if you can solve it. I'll give you a hint even. You don't need logarithms till like the last step. You can actually solve it almost completely without logarithms. So take a screen cap of that and be happy I didn't put one like that on your test there last week, because it's actually pretty gnarly. But it solves. It does solve. It has a real number answer. Okay? I said answer, so I'm kind of giving a hint. There's only one answer that works. Somebody remind me on Friday that we'll solve that together. It's a beautiful little puzzle. Okay, so there we go. The whole point of me revisiting the 4x4 puzzle was to introduce you to my friend right here, the factorial. As I said in the blog here, let me go to the blog. Chapter 11 is about counting. After all the crazy math we've done this year and all the fancy graphing and algebra and weird trigonometry, we're going to end with counting. Isn't that a nice way to end the year? There's a little bit of algebra, but not much. Certainly there was more algebra in the last unit we just did than the one we're about to do. So let's go to the first lesson in chapter 11. Again, this is about page 6 in the booklet. For those of you who joined us late, it's this booklet right here. Notebooks. Everybody got this before you all went away for the COVID break. So here we go. We're skipping 10.3 for now. We'll come back to it at the end if we have time, because chapter 11 might be a little more important. More people take statistics and combinatorial math than take calculus at the university level. So this is an important chapter that we want to make sure we get through. All right, the fundamental counting principle. You can choose one of 3 salads, Greek, Caesar, and pasta, and one of 3 entrees, curry, hamburger, or sushi from a menu. How many possible combinations of meals of 1 salad and 1 entree can you order? We would like to make a complete list of all possible meals. So let's do this systematically. Let's say we order Greek, then the curry, Greek, and then the hamburger, Greek, and then the pasta. Okay, that takes care of all possibilities involving a Greek salad. Then how about a Caesar salad and curry, a Caesar salad and a hamburger, a Caesar salad and I just realized this is supposed to be sushi, not pasta. Pasta is one of the salads, sushi. So Caesar salad and sushi. And then I could get the pasta salad and the curry, the pasta salad and the hamburger, or the pasta salad and the sushi. So that's it. I think I've exhausted all possibilities, and that's 9 combinations. That was kind of a drag, wasn't it? It's a good thing this wasn't the Cheesecake Factory. Anybody actually been to a Cheesecake Factory? I used to think that was like a made-up restaurant that they made up on the Big Bang Theory. And then when I was in the States, they finally opened one in Minneapolis, and I got a chance to go to it. The menu is like a phone book. I've never seen a menu that big in my life. There's literally hundreds and hundreds of dishes that you can order. How can they keep that much food in one kitchen? It boggles the mind. It's not a great restaurant either, I should probably tell you. But what if there was 25 options for salad? Just salad alone, and then 13 different entrees. Imagine how long this method would take us. There must be a better way. It's like I'm selling you something on late night TV. There must be a better way. So there is. The fundamental counting principle says that if one task can be performed in A different ways, and another task can be performed in B different ways, then you can perform both tasks in A times B ways. So if there's 7 salads and 9 entrees and 5 desserts, the number of possible meal combinations is 7 times 9 times 5. And of course, naming all 315 meals is impractical unless you want to make a Cheesecake Factory menu. Let's use this to calculate some stuff. How many license plates could there be here in Manitoba? Well, for those of you who don't know, a license plate is 3 letters, then 3 digits. We'll ignore things like vanity plates and government plates. So the first letter, there's 26 letters in the alphabet. You could have A, B, C, D, E, F, G, all the way to Z. Let's assume you can repeat letters. So there's 26 things you can get for the second letter. And then there's 26 things you can get for the third letter. Now, for the digits, there's 10 different digits. You might be saying, well, isn't it 1 to 9? Well, 0 is a digit, right? You can have a 0 on your license plate. And, of course, you can repeat the digits. So we're looking at 17,576,000 possible license plate combinations. All right, let's try a different example. How many ways can a store manager hire for 3 positions if there's 12 candidates? Right, he needs a stock person and a checkout person and somebody to clean the floors. All right, well, he has 12 different positions. He can hire 12 different people for that first job. But now that he's hired that person, you can't hire him for a different job and make him do 2 jobs. So there's 11 ways to hire for the second position, and then there's 10 ways to hire for the third position. Do you see that there's a logical reason why in example 1 you could repeat the items, and in number 2, the items being people, you can't repeat them. There's a logical reason for that. Nobody has to tell you that. If this was a test question that said, can I put 12 here again? Can I repeat? I'm not going to answer that, right? This one involves you thinking logically, reasonably about how the situation actually would be in real life. How many outfits can you order if you have 4 choices of pants, 5 shirts, and 6 pairs of socks? Well, 4 times 5 times 6. How many ways can I do task A, which is put on pants, task B, which is put on shirt, and task C, which is put on a pair of socks, and 120. And I would like to point out, I'm just copying the notes the way they come from the curriculum. I disagree with this answer, because what if I mix and matched my pairs of socks? But we'll just assume you have to stick to the pair of socks. How many 3-digit numbers can you make with the digits 1, 2, 3, and 4, and 5 if you're allowed to repeat, but B, you're not allowed to repeat? How different will those numbers be? Well, let's see. If I'm allowed to repeat the digits, I'm making a 3-digit number. There's my 3 digits. There's 5 things I could pick for the first number, 5 for the second number, 5 for the third number. So my A answer is 125. My B answer, well, there's 5 digits I can pick for the first number, but then I can't have the same digit again in the second number. So down to 4. Then I can't have either of those 2 digits in my third number, so now it's down to 3, and the answer is 60. Notice there's a fairly big difference between when repetition is allowed and when it's not. All right, notice how often we're going to have things like this. Consecutive numbers multiplied together, and that's why we need a symbol for it. Let's say you want to arrange 6 people in a row. How many different ways can that be done? Well, you could put, you have in the first place on the row, you have 6 different people you could pick, then 5, then 4, then 3, then 2, then 1, 720 ways, and we can rewrite this as 6 times 5 times 4 times 3 times 2 times 1 as 6 factorial. We say 6 factorial, 7 factorial. If you want to actually figure that out, that's basically 720 times 7, which is 40. 4 factorial is 24, which we kind of found out already from our puzzle. And then 18 factorial, try that in your calculator. Your calculator is going to spit out a number so big that it's in scientific notation. It's 6.4 times 10 to the 15. In other words, it's a 16-digit number that begins with a 6. I don't even know, what would that even be if you wanted to name it? 9 digits is billion, 12 digits is trillion, 15 digits is quadrillion, so that'd be 64 quadrillion. Blech. In general, we define factorial notation for n as an element of natural numbers, where n as a natural number factorial is n times the number that came before n, times the number that came before that, times the number that came before that, all the way down to 3, 2, 1. And of course, you don't include 0. Oddly, we do separately define 0 factorial as 1. It's a definition. It's not based on proof. I can prove to you why, for example, x to the power of 0 equals 1. That can be done by proof. 0 factorial equaling 1 is not something that's provable. It's something we define and then use. Yes, 69 factorial is the highest that a calculator tends to go if it's a normal everyday calculator. If you wanted to use, let's see, if you wanted to use our powerful graphing calculator, let's break out the rabbit. If you're looking for factorial, I think on this calculator it's under math. Let's see, can you do 99 factorial, which would be 99 times 98 times 97 times 96 all the way down to times 1? I don't think you can. 99, and it's under number, it's under probability. There it is. It's probability 4. There we go. On most calculators, it's not that many buttons to find factorial. Nope. Overflow. Too big. Let's go to it. Okay, let's cut it down. What if it was... Okay, we know it'll do 69 because that's what most calculators will do. There we go. Yeah, notice 70 would bump this over the 100 mark for scientific notation, which makes it a bigger than a 100-digit number. So it probably won't do it. 70. Oh, this is a drag. Math. Probability 4. No. So there it is. Even on the big fancy calculator, 69 is the winner. So we can play with this stuff. 11 factorial divided by 9 factorial. You're probably thinking, wait a minute. 11 factorial is going to be some number in the thousands. It's huge. And you expect me to do this without a calculator? Yes, I do. Because I want you to think, isn't 11 factorial 11 times 10 times 9 times 8 times 7 times 6 times 7? Wait a minute. That's 9 factorial. Look at that. No calculator required. 110. Aha! Let's do that again for B. 5 factorial, I'll just leave alone. But isn't 7 factorial 7 times 6 times 5 times 4 times 3 times 2 times 1? And I can simplify the 5 times 4 times 3 times 2 times 1 to 5 factorial. There we go. No calculator required. Isn't that cool? Now let's do it with algebra. What do I know about n factorial? Well, n factorial is n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5. But basically, just like I stopped here and said, well, it's factorial from there on out, it's factorial here on out. So that's going to be n squared minus n. Okay, let's think about this one logically. N plus 1 factorial is itself times the next smaller number, which would be n, and then times n minus 1 times n minus 2. But I can stop there and put a factorial on it. And there we go, n plus 1. Check it out. Okay, so here's an interesting one. Prove that 5 factorial minus 3 factorial is 19 times 3 factorial. Okay, well, I'm going to take the left-hand side. And I'm going to say, all right, well, 5 factorial is 5 times 4 times 3 factorial. And then I still have minus 3 factorial. And I'm going to factor out the 3 factorial, giving me 5 times 4 minus 1, which is 3 factorial times 19, which equals the right-hand side. Prove. All right, let's look at number 3. N factorial over n minus 2 factorial. N factorial is n times the number that comes before n, times the number that comes before that, times the number that comes before that, forever and ever. So I might as well slap a factorial on it. All over n minus 2 factorial equals 30. And then, okay, now I'll leave it to you. What do you know about n? N has to be a natural number. So there's no decimals involved. So feel free to guess and check. A number times a number 1 smaller is 30. It's got to be 6 and 5, right? Let's say you didn't know that. Let's say that the numbers are too big for you to play with that way. You could, of course, solve it using factoring. And then, of course, you'd get n minus 6, n plus 5. But this, okay, I'm out of room. You can just write over here or something. N equals 6 is the only answer that makes sense because n can't be negative 5 because we already said n has to be a natural number, so that's extraneous. Again, if you don't want to do it with the factoring, once you got to this step, you can of course just use logic and determine that n must have been 6. Okay? But using quadratics works too. All right. Now, what do we use this factorial stuff for? We use it to calculate things called permutations. What is a permutation, you ask? Well, a permutation is an arrangement of a set of objects in which the order of the objects matters or is important. It's called a permutation. So it's basically, the shortcut for permutations is number of possible arrangements. For example, how many ways can you arrange 4 people sitting on a bench? That's a permutation. How many ways can you choose a group of 4 from the class is not, because it doesn't matter what order I choose them, I've still got the same 4 people. So if the order matters, it's called a permutation. If you have n distinct items and r of those items are taken and arranged, the number of permutations is this formula. The number of permutations is n factorial divided by n minus r factorial. And this is the shortcut way of saying the formula. Subscript n, capital P, subscript r. So for example, if you wanted to arrange 3 books in a display case, but you have 7 books to choose from, you have 7p3, which is 7 factorial over 7 minus 3 factorial, which is 7 factorial over 4 factorial, which is 7 times 6 times 5, or 210 ways. All right, let's start evaluating some of these. Let's use the formula. 6p4 is 6 factorial over 6 minus 4 factorial, which is 6 factorial over 2 factorial, which is 6 times 5 times 4 times 3 times 2 factorial over 2 factorial, and that's 360. All right. Kind of didn't give myself enough room to do number 2 here. Let's do this one. NP2. So n is an unknown. N factorial over n minus 2 factorial equals 30. Does that look familiar? We just did this example. Here's a new one. We have n factorial over n minus 3 factorial equals 120. Okay, so that's going to be n times n minus 1 times n minus 2 times n minus 3 factorial all over n minus 3 factorial equals 120. Those guys cancel. So that leaves me with n times. So again, you can either guess and check using logic, since you know n has to be a whole amount. What number, when I times it by the number 1 smaller times the number 2 smaller, gets me to 120? And 120 is 6 times 5 times 4, so n had to be 6. Feel free to multiply that out, get a cubic, and then use your skills from earlier this year on solving that cubic. But that would work too. All right, let's do a word problem. I have 12 basketball players. 7 must be arranged on the bench. The other 5 can just go home. How many ways can you arrange the players on the bench? So that's 12 permutation 7, which is 12 factorial over 12 minus 7 factorial, which is 12 factorial over 5 factorial, which I'm going to need a calculator for. So I will punch on my calculator. Come on, rabbit. There you are. I will punch 12 math. Oh, this is a drag. 4 divided by 5 math. 4 equals, and there you go. 3 million, no, 33 million, yeah, 3,991,680. Holy cow, do the numbers ever get big. Isn't that amazing? Arranging 7 people and I had 12 to choose from, and there's over almost 4 million ways I could do it. Can I point out to you that most scientific calculators actually have a permutation button, so I could have just entered it right from here. Let's see if I can find it. Clear everything. 12, and then go to math, and go to probability, and there it is. See that? NPR, hit 2, and then 12, NPR 7, and let's see if that's the same answer. I think it is. Yep. If you have that kind of button on your calculator, by all means you can use it, or you could just do 12 factorial divided by 5 factorial. If anybody's rocking an old TI-30XA, I think you even that kind of fairly inexpensive calculator. Can you see on the camera? People who are watching this video at home can't see this, but if you take a look, your factorial button is Shift 3 right there. Your NPR button that I just used on the fancy calculator is Shift 9. So if I was doing the same calculation we just did, I would go 12 Shift 9 7 equals, and boom. That's how you do it. Okay. Oops. No, I don't want help. I want the calculator to go away. Close. Okay. Now it looks like we're at the end of the lesson, but I actually want to go further than that for the first lesson. Let's do some actual word problems here. Permutations with repetitions. Imagine that the letters of the word book are written on tiles. Anybody ever played Scrabble? Imagine that you have B-O-O-K for Scrabble tiles. We want to rearrange the tiles. Have you ever noticed that Kobo is a permutation of book? Isn't that clever marketing? Sure. That's why Kindle pretty much drove Kobo out of the market years ago. But anyway, how many arrangements are possible? Well, let's see. I could spell it the way that you'd think, book. But here's the thing. I've got 2 different O's. So I'm going to call this O1 and this one O2. And then I could respell it like that. That is, in fact, a different arrangement. But It's still the same word. Okay? Let's keep going. Let's do all of the ways I could have B first. So B's first here, and then the first O, and then the second O. I could have B, and then the first O, and then the K, and then the second O. I could have B first, and then the second O, and then the first O, and then the K. I've already got that one. I could have B first, then the second O, and then the K, and then the first O. And then, of course, I could have the B first, and then the K, and then the first O, and then the second O. Or I could have B first, and then the K, and then the second O, and then the first O. There. That's all the possible ways. So there's 6 ways with B first. So how many letters are there? 4. So it's 6 times 4, which is 24 combinations, which is, I kind of knew this already, 4 factorial. Right? How many ways can I arrange 4 things? 4 factorial. Now that we've written them all out, no, I didn't bother writing them all out. Pretend I wrote them all out. We should notice that many of the arrangements are identical, right? Kobo and Kobo with the 2 different O's switched still is the same word. So although we have 4 factorial permutations of the tiles, the 2 O's means that there are 2 non-distinct versions of each permutation. How many distinct permutations? Distinct means different from each other. Well, it would be 4 factorial divided by 2 factorial, which equals 12. In general, a set of n objects with a objects that are identical can be arranged in n factorial divided by a factorial ways. In general, again, if I have n objects with a that are identical, b other identical objects, and c other identical objects, I get this formula. N factorial divided by a factorial times b factorial times c factorial. So, how many ways could I arrange the letters of the word Manitoba and get a different word? Doesn't have to be a real word. Doesn't have to be a real word. It can be just nonsense. But a different arrangement of letters that is distinct. So there is 8 letters in Manitoba, and there's 2 A's. So 8 factorial divided by 2 factorial. That is, I already punched this in the calculator. I'll save you the button punching. 20,160. How many different arrangements of all of the numbers in this could I make? I have the number 81,818. How many different arrangements of those digits could I make? And again, different means unique, so that it's actually a different number, right? If I just switch these 2 ones, that's still the number 81,818. It doesn't look like a different number, and it doesn't read like a different number. How many different numbers can I make? Well, there is 5 factorial numbers. 1, 2, 3, 4, 5. I can rearrange those 5 digits, 5 factorial, 120 ways. But there's 3 factorial 8s. So this is digits. Times 2 factorial 1s. And when I do that, that one I can do without a calculator. 5 times 4 times 3 factorial, all over 3 factorial times 2 times 1. And 2 times 1 is still 2. 3 factorial cancels 3 factorial. 2 goes into 4 twice, and the final answer is 10. Anybody not get how I did that? All right. Check this out. At first, this does not look like it's the same kind of question, but it is. How many different paths can you follow from A to B if you can only move up and to the right? So you can't, for example, go like this and then back that way. Nope, can't do that, can't do that, can't do that, can't do that. No. You are only allowed to move up and to the right. So, for example, I could go to here, and then to here, and then to here, and then to here, and then here, and then here, and then here, and then there, I've made it. Interesting. All right, let's see if we can count. How many ways, this is about counting. If I go up first, I get to here. If I go to the right first, I get to here. How many different ways can I make it to this dot? Well, there's only one, right? I could just have to just go that way, because I'm not allowed to go back to get that way. There's only one way to get to this dot. How many ways is there to get to this dot? Well, once again, there's a 1. How many ways can I get to this dot then? Well, the answer is 2. because I could go up first, then right, or right first, then up. So there's 2. Now, how many ways could I get to this dot? Well, if I just kept going in this path, there is 1 way to get there, right? Because, again, I can't go to the middle and then come back to the left. I'm not allowed to go left. I'm only allowed to move up and right. So basically, there's only 1 way to get to all of the dots along here. And logically, there's only 1 way to get to all of the dots along here. Okay? Now, how many ways is there to get to this dot? Well, there was 1 way to get to this dot and then move over there. There was 2 ways to get to this dot and move over there. So add those together, there's 3 ways to get to that dot. And then there's 3 ways to get to this middle dot here, and I could go up to get to there, or I could have used the 1 way there is to get to here. 3 plus 1 is 4 ways to get to that dot. Anybody see a pattern yet? So this will also be 3, because there's 2 ways to get to this middle dot, and then go to the right, or go to the right then up, so 3. And since there's 3 ways to get to this dot, 3 ways to get to that dot, there's 6 ways to get to this dot. And there's 10 ways to get to this dot. And there is 4 ways to get to this dot. And there is 10 ways to get to this dot. Notice I've stopped counting. Anybody see the pattern on what I'm doing? There's 20 ways to get to that dot. There is 20 plus, let's see, hang on. 4 plus 1, there's 5 ways I can make it to that dot. 5 plus 10, there's 15 ways I can make it to that dot. 5 plus 1, there's 6 different ways I could get to this dot. 15 plus 6 is 21 ways I can get to this dot. I'm almost home. 20 plus 15, there's 35 ways I can get to this dot. Finally, I've made it to B. There's 35 ways I can make it to that dot. 21 ways I could make it to this dot. There is 56 ways I could make it to that. Thank goodness this wasn't a bigger grid. There must be an easier way. Once again, I'm selling you something on late night TV. There must be an easier way. How about you count that no matter how you got to point B, you went up 3 times, and you went right 1, 2, 3, 4, 5 times. And now this is exactly the same as these questions here. How many unique ways can I arrange those letters? Well, there's 8 letters, there's 3 U's, and there's 5 R's. So that's 8 times 7 times 6 times 5 factorial divided by 5 factorial. I'll just rearrange that multiply. You can multiply in any order you want, right? 3 times 2 times 1 is 6, and 5 factorial, and 8 times 7 is 56. There, that was a lot easier than my counting method, wasn't it? Not that the counting method wasn't fun, and I don't know, can anybody notice what this counting method's actually turning into? If you turned your head sort of diagonally and looked at it, do you see anything kind of special about those numbers? Suppose I looked at them this way across. 1, 1, and then I'll go across this way. 1, 2, 1, and then I'll go across this way. 1, 3, 3, 1, and then I'll go across this way. 1, 4, 6, 4, 1. Hey, is that looking familiar? Not enough R? Yes, there is. 1, 2, 3, 4, 5. Oh, I didn't write 5. Thank you. 1, 2, 3, 4. I said 5. I didn't write 5 here. Thank you. You're right. Anyway, anybody recognize this pattern? If I put a 1 on top and I draw this around it? No? Pascal's triangle? No, nobody's seen Pascal's triangle before? I'm sure you have. All right, move to the next page. What if we have permutations, counting how many different ways we can arrange things, but we have constraints on them. We have rules. This is an actual example right from your textbook. 5 people, we'll call them A, B, C, D, and E. Alfred, Barry, Charlie, Daniel, and Ernie are sitting on a bench. How many different ways can they be arranged if Ernie is seated in the middle? So we have a constraint. So I'm going to actually just kind of write out my bench. There's my bench, 5 seats. Ernie has to go in the middle. So there's only 1 possible person that can go there. Now from there, 4 different people can go here, 3 different people can go here, 2 different people can go here, one different person can go there. So that is, once again, 4 factorial, which is 24. What if A and B must sit together? I want to arrange these 5 people on the bench, but A and B, for whatever reason, have to sit next to each other. So the trick to this is treat A, B as one person. But AB or BA. So notice, that's like saying how many ways can I arrange 4 people, but then I can switch on each of those choices, AB with BA, and that's going to be 24 times 2, which is 48. Cool. All right, what if A and B have had some sort of falling out and they just refuse to sit next to each other? A and B cannot sit next to each other. Well, I could start kind of playing with where they sit, or I can realize that, wait a minute, if this represents all the ways that they sit together, and 5 factorial would be just how many different ways I could seat all 5 of them, if I subtract those 2 numbers, that would be how many different arrangements they are where they're sitting apart. Does the logic of that make sense to you? That's just such a beautiful little piece of logic. All right, I want you to try some now. You have to arrange 3 different calculus books, 5 different biology books, and 4 different economics books on a shelf. How many ways can you just throw them up on the shelf? Doesn't matter. It could be a calculus book, then a biology book, then another biology book, then an economics book, just randomly. How many different random arrangements are there if there's no restrictions? B, what if they must be arranged by subject area? So I don't care what order, as long as all the calculus books are together, all the biology books are together, and all the economics books are together. And notice I'm not saying that biology has to go first or calculus has to go first. And then C, how many ways can you arrange the books if all the calculus books must go on the right side of the shelf? All right. Now I'm assuming in C that the calculus books are on the right side of the shelf and we don't care about anything else. In other words, are you saying that B still holds where they have to be by subject area? No. I'm going to say no other restriction. Okay? All right. I'll give you a minute to think about that. I haven't done attendance yet, so I'll run attendance. And, I guess maybe I could pause the video while people think about this. Okay, so if you're watching this on video, you can pause the video and try these yourself. All right, we're back. If that wasn't enough time, pause again. All right, so the first one everybody should get. This should be pretty easy. If there's no restrictions, it's just 3 plus 5 plus 4, that's 12 things. How many ways can you arrange 12 things? It's a really big number. 479 million arrangements. How many ways can you arrange the books if they must be arranged by subject area? Okay, so here's the way it works. In the calculus, you could arrange the books 3 factorial ways. And then in biology, you could have 5 factorial ways to arrange the bio books. And then in the economics books, there's 4 factorial ways. But then this is 3 different categories that I can arrange 3 factorial different ways. I should have said subjects, not categories, but you get the idea. And then when you multiply all that out, you get a much smaller number, only 103,680. Now, what do you do for this one? Okay, well, how about you just go, okay, on the right-hand side of the shelf, the calculus books have to sit by themselves, which means that it is 3 factorial, and to the left of that, there's just 9 books that have to be randomly put in. So, yep, How had the right answer. Oops, sorry, said a name, but anyway, the person who guessed it first had the right answer, and my pen just died. There we go. Oops, now, page, what are you doing? All right, and what is that? Did I punch this? You know what? I never bought, I just left it sitting like that. I'm going to have to punch that out. 9 factorial times, I know 3 factorial, 6. 6 equals 2,177,280. There we go. There it is. Pretty cool. I like this stuff. This stuff's fun. All right. Next is cases. Every example we've seen so far is a permutation with one case. But sometimes it's impossible to summarize all possible permutations into a single equation. If you cannot summarize a situation, you must break that situation into distinct cases and the resulting permutations for each case. For example, the letters A, R, T, E, F, Q, U are to be arranged in a row, but the arrangement must begin and end with both consonants or both vowels. And for those of you who don't know, consonants would be, in this case, the R, the T, the F, and the Q, and vowels, remember vowels are the letters A, E, I, O, or U, and sometimes Y. How many ways can this be done? So case 1 is you begin and end with a consonant. So we're making a row of 1, 2, 3, 4, 5, 6, 7 letters. 1, 2, 3, 4, 5, 6, 7 letters. And the first letter has to be one of the consonants, R, T, F, or Q, which means that there's 4 things that can go there. Then this is those same 4 choices minus whatever the choice was that I made for the first one. So a 3 goes there. And then the rest of them can be in any order. I've used 2 of the 7 letters. There's still 5 left, then 4, then 3, then 2, then 1. If I want to simplify this mathematically, it's 4 times 3 times 4 factorial, which is 12 times 24, which is 144 doubled. No, it isn't. It's 5 factorial, not 4 factorial. Thank you. So that's 12 times 120, which is 144 times 10. That's what it is. There you go. There. Don't need a calculator for that one. Now, what if we begin and end with vowels? Same trick. There's the 7 places that the letters can go, but the first letter has to be either the A, the E, or the U. And then the last letter has to be either the A, the E, or the U that's left over. So 2 of those 3 letters. Then there's still, again, 5, 4, 3, 2, 1 numbers that or letters that I have to place in the middle. So that's 3, that's a funny looking 3. 3 times 2 times 5 factorial, which is 6 times 5 factorial, which is 720. So in total, there's 1440 plus 720, which is 2160. Why couldn't I just do that in one big calculation? Well, because the choices for the endpoints didn't have the same sample size for their sets. Okay, I have a hand up. I have a question. Did I lose somebody? This person right here has their hand up. Where did the 5 come from? Okay, so the question is, where did the 5 come from? Let's go back to case 1. There are 1, 2, 3, 4, 5, 6, 7 letters here, right? I have to pick a consonant to go here and a consonant to go here. So that means that I've picked 2 letters. So now out of the 7 that I started with, there's only 5 possible letters that can go in that spot there. Does that help answer your question? And that's where that's the same logic as to how I got a 5 here. And then once I've picked a letter to go here, there's only 4 letters left I have to pick from. And then there's only 3 left, then 2 left, and then that leaves just 1 possibility for there. Does that answer that question? It's a good question. All right, let's try another one. How many different 3-digit even numbers greater than 303 can you make using the numbers? And if you're starting to notice, hey, we're talking about how many different ways you can arrange letters and numbers, we call this branch of mathematics combinatorials. And it has a lot to do with security, password combinations, all that kind of math is very big and very important nowadays, as you might well imagine. Okay, so anyway, what are the cases here? Well, I'm allowed to use the numbers 1, 2, 3, 4, 5, and 6. I'm not allowed to repeat any of the digits. I need a 3-digit even number. Now, even numbers, case 1, I'm going to say ends with a 2. Case 2 ends with a 4. And case 3 ends with a 6. Now you might be thinking, aren't all these the same? No, 2 of them are. Let's show you what that means. We're picking a 3-digit number, and it has to end with a 2. So a 2 goes here, so there's only one way I can pick a 2. After that, all that I care about is that the first digit is 3, 4, 5, or 6. Right? Because remember, my number has to be bigger than 303. So as long as we start with a 3, there's no 0. Everything that starts with a 3 is going to be bigger than 303 in this case, right? So there's 4 possible numbers that can go here. There's only 1 possible number that can go here. I had 6 digits to choose from, so there's still 4 more left I can pick to put in the middle. So there are 16 ways in case 1. Isn't there 16 in the next case? No, because notice if this has to be a 4, I don't have as many choices here anymore. This can only be a 3, a 5, or a 6. You might be thinking, well, but you could put the 2 in there the way the 4 was in there. Yeah, but then your first digit can't be a 2. You wouldn't be bigger than 303. So this one is 3 times 4 times 1. 12. This one's going to work out the same as that one. There's 3 possible places. This one has to be a 6. There's only one 6. But now this can be 3 or 4 or 5. There's only 3 choices for that. There's still 4 in the middle. So there we go. Grand total, 40 possible even numbers bigger than 303 that I can make with the numbers 1, 2, 3, 4, 5, and 6. Isn't 1 an option? Yes, but the 1 can't ever go first because then I'm not bigger than 303, and the 1 can't go last because then I'm not an even number. So the 1's always kind of mired in this middle calculation here. The question that I just got for those of you watching at home was, isn't 1 an option? How come you seem to be ignoring it? Because it doesn't really count in my special kind of counting for the cases. Does that make logical sense to you? All right. These are fun. All right, once again, I want you to try a couple. So, how many different 3-digit multiples of 5, can I make with the digits 0, 2, 3, 5, and 8? And then number 2, if I use the digits 1, 2, 3, 4, 5, 7, how many 3-digit numbers greater than 400 are possible? And then in B, how many of those numbers in A are odd? Okay, so I'm going to, again, pause the video, give you a couple minutes to try it, and then I'll go over them. So let's see, go back and we'll pause. Okay, so pause the video and give this a try. Okay, if you need more time, pause the video again. But here we go. How many different 3-digit multiples of 5 are possible using those digits? The 2 cases are, case 1 would be we end with a 5. And then this could be 2, 3, or 8. Notice I'm not putting the 0 there because if you started with a 0, it wouldn't be a 3-digit number, right? So that would mean there's 3 possible things that can go here. And there was 1, 2, 3, 4, 5 things. I've used 2 of them, so there's still 3 things that can go there. So there's 9. For case 2, now I'm putting the 0 at the end, right? You're a multiple of 5 if you end in either 5 or 0. So there is 4 things that can go here. and then 3 things in the middle, and then 1 possibility at the end. So the grand total is 21. Does everybody get the logic on that? You can't start a 3-digit number with a 0. That would make it a 2-digit number. Number 2, using the digits 1, 2, 3, 4, 5, 6, 7, how many 3-digit numbers greater than 400 are possible? Okay, well, let's see. This one's straightforward. I think you can do this in one case. You have to be greater than 400. Everything here is anything that starts with 4 or more, or 4 or higher, will be bigger than 400. So you could start this with a 4, 5, 6, or a 7, meaning there's 4 choices there, and then there's still 6 more choices to go, and then there's still 5 more choices to go. 4 times 6 times 5 is 120. Straightforward. But how many of these are odd? Well, I'm going to have to count these separately. Case 1, what is it? It ends in a 1. So then that's case, case, case. So if we end in a 1, there's only one 1. And then this can be 4, 5, 6, or 7. So there's 4 choices here, times 5 times 1, so that's 20 choices. But then there's 3 other choices that you could end in, right? You could end in a 3, right? And if you end in a 3, this is still 4, 5, 6, or 7, but this ends now in a 3, and 4 times 5 times 1 is 20. So those 2 are the same. The next 2 are also the same. You could end in a 5 or end in a 7. And notice those are going to be the same because if you end in a 5, this 5 is gone from the choices. And then there's 3 things here, 5 things there, and the 5, so there's 1 thing there. So that's 15. And then this one I'm going to say is ditto. Ditto, except instead of 4, 6, 7, it's now 4, 5, 6. Those are ditto marks, which means it's the same as the one above it. So it's 20 plus 20 plus 15 plus 15, which is 70 choices. All right, and that takes us, that is actually pretty close to everything we're going to do for lessons 1 and 2. The next page is where we start lesson 3. So you can now work on, let's see, go to the blog. You can now go to the first assignment, the 11.1, and actually, it's actually the 11.1 and 11.2 assignment in the chapter 10.3 assignment book. Actually, just stick to the 11.1 for today, because I think, now that I think about it, 11.2 and 3 are actually mixed into one assignment, I think. So it's just the 11.1 assignment you can start. Here's what it looks like. Again, I put the 10.3 assignment first in the booklet, which we're going to do at the end. So skip this assignment for now. And you are now there. No, not that one. The solutions. There. 11.1 assignment. So you should be able to do pretty much all of this one up to number 19. And then, yeah, and we'll start combinations tomorrow. Okay, so there we go. So get some of that started. And okay, let me stop my video. Thanks for watching.